this is the JIT for week 2, and the idea is to initially review essentially the things about buoyancy forces and Bernoulli equation that were covered in last week's JIT in readings 3 and 4. So there are several problems that are associated with this. First one says, you and your friends step into identical rowboats. You notice that your boat sinks into the water twice as far as your friend's. What can you say about your friend's weight compared with yours? And there are various options here. Your friend weighs twice as much as you do, half as much, the same as you do, or 1/4. And the idea is that yours sinks in farther, and so the idea is that the buoyancy force clearly is larger because you're displacing more water. Let's try this. This thing's a bit fussy. So the idea is that you have a boat, and we'll assume it's a rectangular boat. And the idea is that the total weight, if it's floating, has to be essentially supported by whatever the buoyancy force is. And so when you add a mass into it, of course, it will sink larger, down in more, so that actually you increase the buoyancy force. Let's sort of ignore the weight of the boat itself and just assume that we have a person of mass m that's being supported by the buoyancy force. Then the idea is if this has some sort of a cross-sectional area, let's assume it's a rectangular boat. And so it has some cross-sectional area, then the idea is that the depth, let's call it h, that the boat sinks down into, basically is what's displacing the amount of water. And so the volume of the water that's displaced is just the cross-sectional area of the boat times h, which means that the mass of the water, which is displaced, is the density of the water times the volume of the water, or A times h. So clearly what happens is if h gets larger, then it means that the mass of the water that's displaced gets larger. And so B is essentially just rho of the water times A times h times g, because it's the weight of the water that gives you that buoyancy force. And so if you look at the free body diagram, then if it's stable, then the sum of the forces have to be equal to 0 so that it's stable, which basically means that the buoyancy force is equal to mg, which is, if we ignore the weight of the boat, it's just the weight of the person. And so mg is equal to rho water A times h times g. The g's drop out. And so the point is if the h is 1/2 of what it was, then the mass is half. If h is twice as large than it is, then m is twice as much. So the appropriate answer for this guy is that since your boat sinks in twice as far as your friend's, it means that your friend weighs half as much as you do, which is basically B. The second one says, as a cube of some unknown material floats in a freshwater pool, half of the cube is out of the water. What is the density of the material compared with the density of the water? And it gives you various options. So let's do this. Let me get rid of this drawing. And so again, it's pretty much the same thing. You've got the water. You've got a cube, which presumably has, every side is basically equal. And so it floats down basically so that 50% of it is exposed. The volume of the cube, if each one is a side d, is that the total volume of the cube is equal to d cubed. But what that means, though, is that since 50% of the water is displaced, it means the volume of the water that's displaced is just half of the volume of the cube itself, which is basically d cubed divided by 2. Or if you wanted to look at it this way, it's basically d squared times d over 2. And so this is the volume of the water that's displaced. And again, what you have is that you have a free body diagram, and so the buoyancy force has to support somehow the weight of the object. And so what you get is that, if I wanted to draw these things, is the weight of the object is just the density of the object times its total volume, which, as we said, is d cubed. So it's the density of the object times d cubed. On the other hand, the buoyancy force, which is the weight of the water displaced, is rho of the water times basically half the volume, which is basically rho of the water d cubed over 2. And so, since Newton's laws basically says the sum of the forces, it means that the buoyancy force minus the weight of the object has to be equal to 0. That means essentially that the buoyancy force is equal to the weight of the object. And so what you end up getting is the weight of the object, actually there's a factor of g that's missing here, is, and the weight of the buoyancy force is just d cubed over 2 times rho of the water times g. And then on the other side, what you have is that you've got the mass, the weight of the object, which is the density of the object, the unknown density that you need, times the total volume of the object, times g. And so the g's drop out, d cubed drops out, which means essentially that rho of the object is just equal to rho of the water divided by 2. And so if rho of water is 1,000 kilograms per meter cubed, then rho of the object is 500 kilograms per meter cubed. And so the unknown density basically is 1/2 that of water, which means that it's C that's the appropriate answer.